Chapter 8, Holiday and Resnick, Problem 13. A 5-gram marble is fired vertically upward using a spring gun. The spring must be compressed 8.0 centimeters if the marble is to just reach the target 20 meters above the marble's position on the compressed spring. What is the change in the gravitational potential energy of the marble Earth system during a 20-meter ascent? B, what is the change in the elastic potential energy of the spring during its launch of the marble? What is the spring constant of the spring? Well, A, we don't need any knowledge of the spring to solve A, because we know that it ascends 20 meters and we have the weight of the marble. And we know potential energy as it deals with gravity is equal to mgh. The potential energy is stored in the gravitational field at 20 meters. So we just have the marble, which is 0.005 kilograms times 9.8. I'm leaving the minus off because we're going to take up as positive. Up is in the positive direction, and down we'll take in the negative direction. And times the height, which is 20 meters, and we get 0.98 joules for the potential energy at 20 meters. Now B asks, what is the change in the elastic potential energy of the spring during its launch? We know that 0.98 joules. It must be the same energy that the spring has when it's compressed. We know that because we're dealing with conservative forces and the energy is conserved. So since we're compressing the spring, and if you know that you could sort of almost guess it from the fact that F equals minus kx, that we get a minus sign, and also we got that minus sign. But anyways, since we are compressing the spring, we're going to get minus 0.98 joules. This is just an example here. Don't take it too serious. All right, so we're going to get 0.98 joules for B. Now C, what is the spring constant? So we know the potential energy is equal 1/2 kx squared. And we'll just go to K is going to equal 2 times the potential energy over x squared, just like the last problem we worked. And we know the potential energy is 0.98 joules, so 2 times 0.98 joules divided by x, which is the compression of the spring, which is 0.08 meters squared, and that's going to equal, it's going to equal 306.25 Newton meters. We could just take that to be 3.1 times 10 to the second Newton meters.